All right, I'm gonna get started. So you guys are here for the FEA Milestones course. I think everyone knows that, but I'm Bernardo. And then that's George. We're gonna be instructing this course, and we'll go into bio. So I'm a sophomore in mechanical engineering, and I'm from Brazil. And then my experience in CAD is Fusion 360, SolidWorks, NX, and then a little bit of Inventor as well. And as far as my experience in FEA goes, it's just Fusion 360. I've played around a little bit with ANSYS Fluent, but I'm not very good at it.
Yeah, I'm George. I'm a sophomore in aerospace, and I'm from Indonesia. My experience in CAD and FEA is very similar to Bernardo, with the exception of not having Inventor there. I've also like tried to mess around with ANSYS Workbench, but it's a lot more complicated and not user friendly compared to Fusion 360. But we're not going to talk about that. So, yeah.
Okay, so I'm gonna put this on there, and I'm gonna say a couple of things while this is on there. While you guys just go ahead and scan that. So every week, we'll have a lecture from 5:30 to 7:30 in here. And with that lecture, I'll always put up an attendance QR code, which will also be shown on the recorded video, which we'll post to the YouTube for the Purdue ASME YouTube later, and I'll send you guys a link of that through Slack. And then with that, I'll also send the attendance link out and the weekly assignment submission link. For this first week, there is no assignment. It's kind of more of an intro week. But a couple of things with assignments, we will not be accepting late submissions. We'll make it clear when assignments are due. It will most likely be 11:59 p.m. Tuesdays before class, the day before class. And for the final project, it'll be slightly earlier than that because you guys will have plenty of time to work on it in class. With the assignments, if you guys have any questions about assignments, obviously when you're here, just ask. But if you're not in here, please Slack us either individually or both me and George, or in the general or the assignments Slack channel. One of us will be able to respond and answer your guys' question there. What else? Yeah, grading. We will try to have your guys' assignments graded by the next class, and when we kind of release the scores, it's basically a completion grade to get the certificate. So in the Google Forms, it's like a quiz. So your actual assignment submission question that you upload a PDF to, when we release the scores, you'll get an email sent out that will basically say like, hey, this is your score. And then we'll have a little bit of individual feedback on every person's assignment in there. So if you didn't get this, and you're just walking in, like I said, I'll put it up again at the end and I'll send it out later as well. Anyway. All right, so if you guys have not taken a Milestones course before, quick intro onto that. It's basically a series of skill-based workshops that supplements coursework. It's 0 credit hours, so this won't affect your GPA. And at the end, you're going to get a certificate, just right there, sent out to your Purdue email. It's for this session, it will most likely be about mid-June to late June, July, kind of in that time frame. Yep. Okay, so in the course objectives is to understand FEA and the finite element method empirically, which is what we'll go over kind of today. And then have the necessary tools to actually perform FEA on a computer. In this case, we're going to be using Fusion 360. If you don't have Fusion 360, by the way, please download it. We will run through how to download it if you guys need help with that today. But it's going to be really important to have that. And then we're also going to learn how to display results in a meaningful way so that you guys can understand what the computer is actually telling you. And then the final part, which is what we'll learn in week 4, is basically shape optimization. So how can we improve the model based on the simulations we have run? So the course structure is 5 lectures, 5 modules. Those are just the names of each of them. Today is the intro to FEA and just the general Fusion interface. And then basic skills will be next week. We'll actually learn how to do an FEA analysis next week. And then the third week we'll do mesh improvement, which is a big factor of learning the FEA. The fourth week is, like we said, post-processing. That's kind of understanding your results and then also doing shape optimization. And the final week is just a project work week. Like I said, one course project, those are the dates. If anyone wants to write them down. We do not have class spring break. It's this week, next week, spring break, and then 3 more weeks. And then the course project description is basically to create a model and then perform a shape optimization on that model, and then suggest a design improvement, which we'll talk about more on how to actually do that. And then you're going to be able to run a simulation to kind of prove that that design improvement works. So going into the actual module. So what is computer-aided engineering? It's basically using computational power, your computer, to simulate approximations of real-life problems. In this case, it's going to be FEA, but you could also have computational fluid dynamics, which is abbreviated to CFD usually, and a couple other different things. And what is FEA? It's basically simulating a given physical phenomenon by using the finite element method, which is a lot of complicated equations, which you guys won't have to learn. We'll kind of go briefly into what that is. But basically your computer will do those calculations for you, and then give you results based on that. And there's a bunch of applications to FEA. You can have static analysis, which is what this course will focus on. You can also have dynamic analysis, Buckley analysis, and modal analysis. And that's what your results will look like when you run a simulation. So what's the difference between FEA and fluid mechanics, which is basically CFD, like I mentioned? So CFD focuses on the surroundings of the object, and FEA focuses on what's actually happening on the object. That's kind of mainly it. The main things we're going to kind of discuss in this class are the von Mises stress, which is we're going to ask for specific screenshots and assignments, and it's basically going to be showing the stresses, the strains, and then also the displacement that will be shown on screen. Yeah, and so similarly to FEA, CFD uses FVM, which is the finite volume method. It's very similar. It's just those are the equations that describe what happens surrounding an object. I'm going to open this full slide. So confusing. So basically, the finite element method is a way to describe a physical phenomenon using mathematics, and it's mostly described using partial diffie-qs, which some of them don't actually even can't be solved. Like you have to use loss and estimations and things like that. And basically these would take forever to do for a part, but your computer is really fast at doing calculations, so it can do it really fast or relatively fast. But yeah. And then with that, you can predict the behavior of a part, whether it'll fail, it'll deform, things like that, under specific conditions that you will input into the program. So I want you guys to think about the way you calculate the area under a curve. You basically just grab little squares, right? I'm pretty sure everyone's seen this video. You grab little squares and you make them smaller and smaller and smaller until you get a really good estimation of what's actually occurring, which in this case would be the area. So basically with FEA, we're going to be doing that, except over the surface of a part or a model. And then a little bit about the history of FEA. Just go through. This is not that applicable to this class, but it's in there. Basically, those three that are listed up there, they basically describe the mathematical equations, which are known as the finite element method. And then those right there are listed as basically the ones who kind of translated those mathematical equations to actually being able to use computational power to solve those equations. So the FEA like today. And then applications to FEA can be many different things. The main things it's used for is understanding what happens in vehicle suspension elements, in wing structural components, in building structures, specifically with beams like I-beams, Y-beams, things like that. And then a little bit with shape optimization, time efficiency, cost reduction, and then also iterative design improvement, which can happen. I'm going to go through the available FEA software. There's way too many of them, but there's every single CAD manufacturer has its own, like it has for CAM as well. The one we'll be using obviously is Fusion 360, and everyone likes to hate on Fusion 360 because it's too simple, but it's simple for a reason. It's so people can understand how to use it, and then from there kind of go off into other programs like ANSYS, like we said, ANSYS Fluent, ANSYS Workbench that we mentioned. Those are much more complicated to use. And then there's also, SolidWorks simulation, and then the Siemens one. So with the finite element method, there's a lot of things that go into it. Just open all those. Also, this first lecture is very much us talking at you. I promise the next few ones are more hands-on, and you'll actually have examples to do in lecture. So just bear with us for this first one. So the main stages of the finite element method, the first thing you have to do is you have to make your model, like kind of break it apart into smaller sections. That's like how we describe the area under a curve. That's basically what we're going to be doing here. And this is basically just called meshing. Like we said, the third week, you're going to have mesh improvement as kind of the main topic. That's something that really plays a part into what your simulation will do in Fusion 360. So this is a really important part. And basically, every equation that governs what will happen to that part will be solved for each individual portion of it. So you can see up here that there's the actual model, and then this is a mesh overlaid on top of the model. So basically what Fusion will do is it will run the simulation, the calculations for every single little model right there. And it'll be able to kind of precisely understand what's happening at that point. And then it kind of brings all of those little points together to be able to understand what's happening to the entire part. And like I said, how big or small the parts you're actually analyzing the equation on can change the accuracy of your simulation. And for most of the times, areas that are smaller or more dense or have curves, things like that, we want a smaller element size so we can be able to understand more accurately what's occurring right there. So this just goes through showing the actual model, and then it'll walk through the mesh getting finer and finer as it goes. And it can get really fine. Like that one, you can barely tell that there's a mesh on there. The finer you get with the mesh, the more time it will take to run that simulation. So this one here, we've run a simulation with this. It takes about 5 minutes to just generate the mesh, and like 20 minutes to 30 minutes to actually run the simulation. So it all depends on how much you actually want, how accurate you want the simulation to be. There's something called convergence, which basically is just showing the difference between one value and the next, and how close you are to that actual point. So say you want, say you know that the force exerted on, or the stress exerted on that specific little portion of that element is going to be 0.5 MPa, right? Basically what the simulation will do is if in one iteration it's 0.500 MPa and the next iteration is 0.5000001 MPa, you know that like what's the point of running the second simulation when we're basically going to get the same result as the first, and it's going to take say like 20 more minutes. So that's something that we're going to talk about in this class. The next part that you need to do is you need to define the materials and their properties. Fusion actually has a really good library of materials. So the main one we're going to be using for this class is aluminum 6061. And again, we'll mention that again when we go into assignments. But basically the important things to know from the actual material properties are the density, Young's modulus, Poisson's ratio, and there's a bunch more like yield strength, ultimate strength, things like that. And like I said, they're usually preloaded from a library. If you don't find one specific that you want to use on Fusion 360, you can usually download them. I think Bechtel has some special materials of their own in their like Fusion drive as well. The next part would be to define boundary conditions. These can be things like forces applied, which doesn't necessarily need to be a force. They call them loads because it could be a pressure, a moment, things like that. And then you also need to define constraints. So if you have the part that we use, that wrench, we're going to constrain it basically on one end so that it can't move. And then we're going to pull it on the other end and show what happens with that. Yeah, and with the constraints, there's different types. We're only going to be using fixed in this class, but you can do pin, frictionless, rod. And I believe there's one more type in there that's not mentioned. And then contacts are important in the case of assembly. We don't go into assemblies in this class. there are two things you can do with an assembly. You can either make it a rigid body, which is very inaccurate, but it can be useful when you're just trying to run a quick simulation. Or you can use contacts, which kind of simulates what would actually happen with an assembly. Say you have like a nut and you have a rod going through it, you can actually simulate what will happen with that. And then this part will not be applicable in this class, but you sometimes need to define initial conditions if you're running a simulation. And then this is what a kind of material property would look like. It would show up, we'll show you where this is in Fusion as well. Okay, so this part is basically just saying that you're going to solve the equations. Fusion does this part for you. Again, this is running through the actual method of how to do it, but yeah, Fusion basically uses Laplace and a couple other different things to estimate what would actually happen on those elements. And then the last part is visualizing your results. You're going to get color scale plots, which is like that colorful picture I showed you guys at the beginning. And you can get that from various different things: stresses, displacement, safety factor, which is an important one as well. And then you can actually animate what will happen when the force is applied. And then one other thing that you can show in Fusion is when you show the deformation that default pops up is really exaggerated because some of these displacements are 1 × 10⁻⁴ millimeters. So the human eye can't really like see that when it's actually there. So it exaggerates the deformation. There is a mode to switch it to actual or completely undeformed, which is the original part. And then the other thing you can do is specify minimum and maximum values for whatever parameter you're looking at, as well as drop like point nodes. If you want to understand what's happening at a specific point in your part, you can do that there. And that's what your result would look like. Yeah, this used to, yep, there it is. It's just very slow video. It kind of shows the differences between it. Let's see it. That's the original model, and then the one that showed up first was the actual result. And there's a couple additional steps. Like I said, we'll go into shape optimization. That's basically how you can just iterate and make a better part. And then there's some separate things you can define, like boundary conditions. Parametric simulations basically take your simulation and run it with slightly different values. We don't go into that in this class. We touch on adaptive mesh refinement, which is similar but not exactly the same. And then this right here will actually pop up when you finish a simulation, and it basically just says that your results are what your results are for your safety factor. And one thing to note, does everyone know what safety factor is? Okay, I'm gonna cover it just in case. But basically safety factor is kind of showing how much your part can withstand. So say your part has a maximum strength that it can withstand, right? It's basically a ratio of the maximum strength and the strength it actually has. And it basically gives you it's a ratio, so there's no units on it. But generally in industry, you want 1.5. 3 is really good in industry. But like you see up there, it says 15. So one thing you could do with that is shaped optimization, where you could remove some of the actual material from the part. Yeah, you would compromise safety factor, but if your minimum, you could say, is 1.5, that's okay. One thing to note, if your part is below 1 max safety factor, that means your part will fail. So at this point, does anyone have questions just regarding general course organization or anything of that sort? Okay, can I do a raise of hands? Who doesn't have Fusion 360 on their laptop? Okay. Today is a shorter class just because we're going just general intro. So as of now, the content itself is actually done. If you want to stay and we can help you download Fusion, yeah, yeah, that's it for today, to be honest. Please wait, hold on. I'm gonna go back to the attendance. I'm gonna send out the attendance as a link in Slack. Also, everyone is in the Slack, right? If you're not in the Slack, I'll include it in the email next week. I'll be sending an email with the slides every week at 5:30 when class starts. So I'll include it in that as well, so you can join again. Or just come talk to us now and we can add you to it. Sorry, this takes a while to go back through. There we go. If you did not get the attendance, it's there. We'll send it out as a link in Slack. And then I'll also link the YouTube video for every single lecture in Slack weekly. So yeah. Leave that up there.